Hello, this video is for Stat 110, Module 3, Part 1. It includes a discussion of the performance order bias case study. Okay, let's go ahead and get started then. So this case study is centered around a singing competition in which they were interested in trying to determine whether or not there was bias in order or due to the performance order of the contestants. So in particular, are individuals who perform later in the competition more likely to win than those that perform earlier in the competition? This study was actually done as part of an undergraduate thesis project at Harvard University. There were 4 different conditions that they used in determining the order in which the individuals that were doing the judging viewed the contestants. So condition 1 was the people that were doing the judging just viewed them in order from 1 to 12. Condition number 2 was that they were viewed in the opposite order. So from contestant 12 went first, and then contestant 1 went last. And then they had 2 additional, which was kind of a mix-up between those 2. So condition 3 was contestant 6 down to 1, and then 12 down to 7. And condition 4 was position 7 through 12, and then 1 through 6. The purpose being that these contestants that were performing in the singing competition were in a variety of orders for the different judges, or the people that were doing the evaluating. The goal of the study was to try to determine whether or not the people towards the end of the competition performed better in the judge's eyes than people earlier in the competition. Now with these different conditions, we can see that contestants 10, 11, 12 performed at the end for condition 1, contestants 3, 2, 1 at the end for condition 2, contestants 9, 8, 7 for 3, and then finally 4, 7, and 6. All 12 contestants were in the last group for all of the conditions. So again, this study was carefully set up to try to tease out whether or not there was performance order bias. They talked about chunking this information into 3s. So that's how the data is going to be analyzed here. So 5 times, as we can see on the screen here, individuals in that were in positions 1, 2, or 3 were considered winners of that competition. There were a total of 29 judges, or people doing the evaluating. So out of those 29, 5 times, the winner was determined to be in one of the first 3 positions. And in fact, they were all in that first position. Out of the 29 times, nobody won in position 2 or 3. Likewise, for the other, in positions 4, 5, and 6, we had 6 winners. In positions 7, 8, 9, we had 8 winners. In positions 10, 11, 12, we had a total of 10 winners. Now again, remember that in the positions 10, 11, 12, all the contestants were present. Okay? So it wasn't just certain contestants that were performing last. It was a mix of all of the contestants that were performing in that last slot. So here we really have 4 sets or 4 slots. Our data that we're going to be analyzing is the 5, 6, 8, and 10. There were a total of 29 judges for this competition, or for these contestants. And here's what the data is that we're going to be analyzing again, the 5, 6, 8, 10. We need to set up a reference distribution under a situation of no bias due to performance order. And if that's the case, we should expect 25% of the winners to come from set 1, 25% of the winners to come from set 2, 25 from set 3, and 25 from set 4. Okay, so there's 4 different sets that we're using for our analysis. There's a total of 29. So 29 divided by 4 is about 7. So we should see about 7% if there is no performance order bias. I think the exact expected value is like 7.25. So that's how this reference distribution was obtained. Was just using the simulation app with the value for p being 0.25 and the sample size being 29. Here's our research question, hypotheses, and the parameters. So the research question is there evidence of serial order bias in singing competitions? Again, we put our research question in the HA. So HA here is that serial order bias exists, and the H naught is that no serial order bias exists. Remember, the H naught is kind of the fair situation or the no difference situation. Here we're going to have a total of 4 parameters. So this is the first time that we've dealt with more than one parameter at a time. So we're going to have a parameter pi sub set 1, which is going to be the probability that the winner is from the first set, pi sub set 2, all the way down through for all 4 sets. Now, if there's no serial order bias, then I would expect my winner to occur equally in any of those sets. Okay, so under no serial order bias, these are going to be set to 25%, 25%, 25%, 25%. Just like we've done before, we can use those proportions or percentages to determine the expected number. That's what I have here in the table on the screen. Again, there's a total of 29 individuals that were doing the evaluation or judging. I should expect about 7 winners from the first set, about 7 from the second set, the third set, and the fourth set. So again, this is the expected number of winners for each of the sets under a situation of no serial order bias. All right, so how do I set up my simulation model? Well, my simulation model is going to have a total of 4 outcomes. So you can imagine a hat that is divided into 4 equal pieces. Each of those represent 25%. I'm going to pull 29 out of the hat because that's how many judges we had. And we can see that for simulation 1, I ended up with a 5, 9, 7, 8 breakdown. Now there should be about 7 or 8 in each set under no performance order bias. And those numbers are pretty close to that 7.25 value there. And they should be because I'm pulling them out of a hat where each of the categories are equally likely to occur. I can pull out a second set. So I got 7, 3, 10, 9 there. A third set, 9, 11, 5, 4. And I can just keep doing that many, many, many times. Now what I'm going to end up doing here is wanting to compare my study outcomes, which again were 5, 6, 8, 10. So that's the breakdown of the observed data. 5, 6, 8, 10. Is that like these or not like these? So if the 5, 6, 8, 10 are similar to what I'm getting from my repeated sampling from this hat, then I'm going to end up saying there's no serial order bias. However, if my breakdown of, again, 5, 6, 8, 10 is far away from these numbers, then I'm going to say that there is evidence of serial order bias, or that the proportions are not all equal. So how do I obtain my reference distribution when I have 4 different sets? Well, I would just have 4 different reference distributions. I would have a reference distribution for the first set, the second set, the third set, and the fourth set. So if I took these first ones and just started plotting those, I would have a 5 for set 1 here. It looks like I have a 9 for set 2. For set 3 here, I have a 7. And then for set 4, I have a value of 8. Again, I'm just taking those from that first simulation outcome and plotting those. And then I would plot the second set. And I would just do that for all 100 sets here. Okay? And that's what I'm going to end up with on the right-hand side. So these values right here are the outcomes from my repeated iterations of running my simulation for the first set here. So these would be the values all down in this column here, the 5, 7, 9, 7, 3, all the way down to the last one would be an 8. I would do that same thing with the second set, the third, and the fourth set here. So that's what we're seeing on the screen. Now these reference distributions all look fairly similar to one another, and they should, because I'm pulling these outcomes from a hat where they are equally distributed across the 4 categories. So these reference distributions are all going to have expected values of 7.25. They're all going to settle down at about the same spot on the left side, and they're all going to settle down about the same spot on the right side as well. Again, because these are generated under a no bias situation, or where all 4 outcomes are equally likely to occur. Once we have the reference distributions, we can use the outlier rule here to lay down what would be an outlier. Or on the right-hand side, we could compute the p-values based on each of these reference distributions. These tests that we're considering here in Module 3 are all 2-sided tests. So for the first set, I had a value of 5. That's what I observed, and that doesn't appear to be an outlier in this distribution. Again, outliers would be values that are below, it looks like 2 or 3, or above 11 or 12. My observed data again was a 5, 6, 8, 10, and none of those appear to be outliers. We're getting kind of on the edge for the fourth set, so we tend to be on the high side for that fourth set. What does that mean in the context of this problem? Is that people that tend to go later or last in the competition, notice that we had the most number in that last position, or those towards the end of the competition. So some believe that going later in these competitions is better, and that perception is probably driven by shows like American Idol and The Voice, where they tend to put the best singers at the end of their shows in order to keep viewership up all the way through the show. So that would be a confounding variable if we were to do this in reality with those types of shows. If they're putting the best singers towards the end, then maybe that's why they're winning and not because of the position that they're in. However, in this study, that's not the case because they scrambled the order in which the individuals performed. Okay, so let's keep moving on here. It doesn't look like any of them are outliers. The fourth set tends to look like it's starting to push that upper edge, but it's not technically an outlier. We could do p-values here, so I went ahead and obtained the p-values up here on the right side for all of those 4 sets. Here's what those p-values would be. Let's go ahead and try to finish up our analysis here. So the question was, is there evidence of serial order bias in singing competitions? I actually have 4 p-values here, which is, we're going to see in a minute, is going to be a problem. My decision rule is if the p-values are less than 0.05, then the data is said to provide enough evidence for the research question. Well, here, none of them are less than 0.05. Okay, what would we do in a situation where some of these or one of these p-values is less than 0.05 or not the others? And in fact, the approach that I've taken here is not technically correct because I'm looking at each of these sets individually. So by comparing 5 on this reference distribution, I'm just looking at the first set. Or by comparing 10 on this reference distribution, I'm just looking at the fourth set. Now those are called singleton tests, where I would just be interested in one reference distribution or using one reference distribution. So this process that we went through up here, although it seemed fairly straightforward, is not the correct process for the research question being asked. This is considering each of the sets individually. And that's not what was being asked. We were interested in the collective serial order bias, or what we call a composite test, where we're interested in not just one parameter, but more than one parameter at a time. So on the screen here, when I have a hypothesis set up in this structure, we call that a singleton test, because I'm only looking at a single parameter. Here would be testing set 1, set 2, set 3, set 4. That's doing that individually. A composite test would be where we consider all of those parameters simultaneously. Now, when we do a composite test, or when I have a single research question, I should obtain a single p-value, or I need to obtain a single reference distribution. Okay, so some general comments here about that. Composite tests are not equivalent to individual tests. Statisticians have not figured out how to convert an individual test into a composite test. In other words, we have no idea how to combine these 4 p-values into a single p-value. Believe me, many have tried. Things like computing an average don't work very well. There are some methods where they use the minimum of those p-values. So we would just use the 16 here in this case. But that has the problem of ignoring completely what the other p-values are. So that approach does not work very well. So again, statisticians have not figured out how to combine p-values from individual tests in order to provide an answer for a composite test. There's another issue as well, and that is a concern about the family-wise error rate that you would have in your analysis. If we compare each of the individual p-values to 0.05, and here we have 4 of them, we would be comparing 0.56 to 0.05. We'd be comparing the second p-value, which was 0.85 to 0.05. We do that all the way through. We're not going to have a 5% error rate when we're done, but instead we're going to have a maximum error rate of 20%. We do not want an error rate of 20% when trying to make a decision about a research question. Again, we want to try to maintain a 5% error rate. But when I use multiple p-values, I'm going to have an explosion or great increase in the maximum error rate for my analysis. Now there is a real simple idea to alleviate this problem, and this is called Bonferroni's correction. Bonferroni's correction says that instead of using 0.05, why don't we use 0.05 divided by 4? So we'd be comparing our 0.56 to this quantity. I can see that I have a typo here in this column. These should be 0.05 divided by 4. The advantage of Bonferroni's correction is that the maximum error rate is going to stay at 5%. So that's a neat little idea, but in practice, Bonferroni's correction does not work very well to alleviate this problem. There's also this notion of the family-wise error rate versus the maximum error rate. And there's a couple wiki sources that I have provided here for a better understanding of those. The big picture here is that we cannot use individual tests to try to make a decision about a composite hypothesis. If you have one research question, we need one reference distribution from which we can get a single p-value from. Okay, so how are we going to do that? Well, the individual that came up with this test, his name was Carl Pearson, did the following. Instead of looking at the individual reference distributions, he decided to look at how far away was each of the observed from the expected. So for this example, the expected again is 7.25. just look at the distance from how far away is this individual outcome from the expected. Do that for set 1, do that for set 2, set 3, and set 4. So do that collectively across all 4 reference distributions. If you look at the one graphic on the right-hand side, you could make a bar graph for each of those sets. 5, 6, 8, 10 again are my observed numbers. And just how far away am I from the expected on each of those? I would take those differences and just sum those up to give me a total distance away from the expected. So again, across all 4 categories, how far away am I from the expected? I would just take those distances and add those all up. Now, unfortunately, there's a canceling out effect that happens when I do that. So I can see if I take these quantities, negative 2.25, negative 0.125, positive 0.75, and positive 2.75, if I sum those up, I'm going to actually end up with 0. The reason that occurs is because that the negative distances end up canceling out the positive distances. So we have to get rid of the negatives somehow in order to prevent this canceling out effect. In mathematics, there's 2 ways to get rid of negative quantities. I can either take the absolute value of those quantities, or I can do the squaring of those quantities. So here I've done that. So I've taken this difference that I saw for the first set and I've squared it here. End up with a number about 5. Take the second set, which is negative 1.25. So just 6 minus 7.25. I'm going to square that. I'm going to end up with about 1.5. And then I just keep doing that for all of the categories here. Now when I get a total, I'm not going to get 0 anymore because I've eliminated the negative values. So I get a value of about 15, or 14.75. I could also use the absolute values, and here I would get a value of 7 if I did that approach. Now we don't need to do both approaches here. We just need one measure of how far away I am from the expected. And the measure that we tend to use here is method 1. Method 1 is more common than method 2. Okay, so how do I decide whether or not that quantity then, the 14.75, is an outlier? Now this is my study outcome. Okay, it's actually a condensed value. It involves using a formula, and that formula is computing those distances squared and then adding them all up. So this acts as my data value as what we were using back in Module 2. I need to determine whether or not that's an outlier. So I need to build a reference distribution for that quantity, for the 14.75. Or if I was using the absolute value approach, I would be building a reference distribution for positive 7 to try to determine whether or not that quantity was an outlier. Now building the reference distribution just involves going back to the outcomes that I had before. Instead of plotting these individual outcomes, what I'm going to do is compute these distances. So I'm going to take the numbers 5, 9, 7, 8, 5, 9, 7, 8 here, and compute those distances, which again are the distances away from the expected squared. And that's what I'm going to get for that first row here, are those quantities there. And then I'm just going to let the computer add those up. So I get a value of about 9. I do that for the second set, 7, 3, 10, 9. What's going to be the total distance for those? After I subtract the 7.25, square them, and add them all up, I'm going to end up with a value of about 29. And I just keep doing that for all of my simulated values, all 100 of them. And then I can plot these total distances here. That's going to be my reference distribution. So again, the reference distribution is obtained in the same way that your study outcome was obtained. I took my values, subtracted 7.25, squared them, and then added all those up. And that can be used, after doing that, that can be used to determine my p-value. So to compute my p-value, I just need to compute how many dots were bigger than that 14.75, bigger than or equal to. Looks like I put 100 dots here. So the value of 14.75 is not very extreme at all. It's well within the realm of the reference distribution. The calculated p-value for this example would be 61 out of 100, or 0.61. Now this reference distribution right here is for combining all four categories into a single value, or by condensing all that information into a single graph. So this would be the reference distribution for that composite test, and this is the p-value for that composite test. So now I can go ahead and make my decision or complete my test. The research question again, is there evidence of serial order bias in singing competitions? My p-value for this test is 0.61. The p-value is not less than 0.05, so I do not have evidence for the research question. Notice I have just a single p-value now coming from this reference distribution. If I have only one p-value or one reference distribution, then my family-wise error rate and my maximum error rate are going to stay at that 0.05 level. So I don't have to worry about the explosion of those error rates when I use a single p-value to evaluate a single research question. You can do the same thing with the absolute value quantities if you want it. So that's part of the comments here. That quantity, the 14.75, that is called my test statistic, or my statistic for the test. This third comment is about the fact that these tests are two-sided. Let me go up here and explain that a little bit. These tests are two-sided because negative values, so values that sit on the left side, let's go back up here and look at this picture here. The values that sit on the left side, okay, so that is what, 2.25 below. When I square them, they get pushed up to the right side. So when I take these negative distances and I square them, I end up pushing them up to the positive side here. So negative 2.25, I square that, I end up with a positive 5.06. This negative ends up being positive as well. So although that I'm computing p-values on one side here, I'm computing the p-values to the right here. This is indeed a two-sided test. So the tests here in Module 3 are a little bit more complicated than what we've had before. The reason these are two-sided tests is because my test statistic involved squaring these quantities. So values that were on the left side, after I square them, get pushed up to be high values here. Values down here close to 0 would mean that I'm close to my expected. So values that are down here near 0 would mean that the observed outcomes are very close to what I would expect under a situation of no bias. Remember, the reference distribution is built under the situation of no performance order bias. So only values to the right would be evidence against no performance order bias. Or only values to the right are going to support the research question. That is a subtlety of this chi-square test that we're learning about here. Okay, there are a few questions down here at the bottom of this handout. I just asked you I gave you a different set from what we observed. So what if the values were 4, 3, 9, 13 instead? I want you to go ahead and do the squaring. See if you can get the total here. and then use that total to try to determine whether or not there's enough evidence for the research question. Okay, that does it then. That does it for Module 3, Part 1. Thank you.